We're going to look at graphing rational functions. This year so far, we've looked at some different types of graphing. Two of those that we looked at first trimester were linear graphs. Those are any type of straight line graph, such as the one seen here. You've done those before. Those are y equals mx plus b ones, where you have a slope and a y-intercept. We also looked first trimester at quadratic functions. Those are those U-shaped or arch-shaped graphs where we looked at finding the vertex, and we looked at different things about those types of graphs. We've looked at some this try as well. We've looked at square root graphs, where you have where we found the domain and range, and we looked at those similar to the one down here. And we've looked at other polynomial functions where we looked at finding zeros. Those are the where it crosses through the x-axis. We looked at minimums and maximums and different stuff like that. Well, today we're going to look at graphing rational functions. To do that, we're going to look at a couple different examples. This first one on your sheet says that a group of students wants to get their favorite teacher, Mr. Domingos, a birthday gift. They plan to get him a gift certificate for a weekend package at a lodge in a state park. The gift certificate costs $150. If C represents a cost for each student and S represents the number of students, then the cost would be $150 divided by the number of students. So if we graph that out, we get this graph over here that looks at the costs of each compared to the students. And you get this different shaped graph. We haven't looked at one like this before. It's almost kind of like L-shaped in its appearance. And it shows different combinations that would make this true. One student could pay $150 up at this point. We could have 150 students, each pay $1 would get it. Or you could have some combination in between, like 25 students paying $6 right here. But if you graph out all the combinations that work, you get this different shape. This is an example of a rational function. And in these rational functions, you get different points, just like you would in any other graph. You can use a table and figure out where the points are located. But what's going to happen is we haven't looked at ones where you have a variable in the denominator yet. And that presents some different problems when you graph, because we can graph a lot of points here, but there's one number we can't put in for S, and that would be that S cannot be 0 because of division by 0. And that's why you see these graphs don't ever actually end up touching 0. It could keep increasing this way, or it keep going this way, but it never actually gets to 0. And that's because of some different properties of rational expressions that we're going to talk about today. All right, so here's some definitions, some things we're going to look at. We've talked about rational functions already. That's a ratio of 2 polynomial functions. And so you always have one function on top, one function on bottom. When we know whatever one's on bottom, it can be anything, but we can't have it equal 0. Because if you get equal to 0, that's division by 0. That's not something that we want. So because of that, when it can't equal 0, if there was a number that ends up equaling 0, that's what we call a domain restriction. Domain restriction is a number that doesn't work because of division by 0. So we're going to look at some examples over here of some different rational functions that would have domain restrictions. And how you find that domain restriction is you take whatever the denominator is and you put it equal to 0. Because by putting it equal to 0, you figure out where that division by 0 happens. So on this one, for example, if we put x plus 3 equal to 0, we know it can equal 0. So the number here that's not in the domain would be x cannot be -3. If it's -3, we get division by 0. Let's look at another example. On this one, x minus 6 can't equal 0. So if we solve it, we know x can equal 6. That's going to give us division by 0, which is a domain restriction. You could have more than one. This last one over here, if we put both parts under the denominator, the both factored parts, x minus 1 and x plus 1, we see that x cannot equal 1 and x cannot equal -4. Those would be two values that give division by 0. Well, what happens at these division by zeros place? Where we have division by 0 is going to tell us something about continuity. Continuity or being continuous, that talks about graphs of rational functions that may have breaks in their continuity or being continuous. Being continuous means you can't, or being not continuous means you can't trace the entire graph without picking up your pencil. The graphs we've looked at so far have all been continuous. Linear graphs are continuous. You can trace the whole thing without picking up your pencil. Quadratics, they're curved, but still you can trace the whole thing without ever picking up your pencil. Square root ones, once you start, keep going. Same with all these ones down here. And the other type of polynomials, they're all continuous. Well, we're going to get to some where maybe there's not continuous. Maybe there's breaks in there. And that happens, or the breaks happen or occur where the values are excluded from the domain, where we have those domain restrictions. So if we look at the ones we had above here, this f of x function would not be continuous at the point. So these above examples are not continuous at certain places. The first one would not be continuous at x equals -3. At -3, it's not continuous. We're going to have some kind of break in the graph. The g of x1 is not going to be continuous at x equals 6. And same with the last one, at 1 and at -4, not continuous. So those domain restrictions tell you where the function is not going to keep going, where there's not continuity. Okay, well, if it's not continuous, what happens there? One of the things that might happen where that breaks the continuity is what's called a vertical asymptote. A vertical asymptote is kind of like an imaginary line that our graph has that our actual function is going to get very, very close to but not touch. So it's a line that the graph of a function approaches but never actually touches due to domain restrictions. This would be an example here. The graph on your sheet shows the function f of x equals x over x minus 3. This x minus 3 part, we know that x minus 3 cannot equal 0. What's in the denominator cannot equal 0. So there's a domain restriction at 3. X can't equal 3. So what is at x equals 3? You can see we have this dotted line. That's our vertical asymptote. So there's a vertical asymptote. The graph's going to keep going closer and closer and closer and closer to that line, but never actually touch. Same thing on the bottom here. It's going to get close, 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 but never actually touch that line. Now, this particular graph, if you look at it, actually has another asymptote. It's not listed. There's actually what's called a horizontal asymptote as well. Horizontal, remember, means going straight across, kind of like the horizon. And if you look at the graph, you can kind of see where it would be. This graph kind of keeps going up and to the left here, and it's going to keep getting closer and closer. Same thing here, it's going to keep getting closer and closer. You can see there is another imaginary line that would be right here. That would be a horizontal asymptote at y equals 1. So there's another horizontal one that it kind of approaches but never touches there as well. All right, well, we're going to have some of these vertical asymptotes. We're also going to have one other type of break in discontinuity called a hole in our graph. And that's called a point discontinuity. Holes occur where you have a value excluded from the domain, but it's a little different than the vertical asymptotes because if you simplify the function, it actually cancels out. Here's an example on your sheet. Graphed is the function x plus 2 times x minus 1 over x plus 2. You can see you got this domain restriction here. We know that x plus 2, what's in the denominator, can't equal 0. So we know we can't equal negative 2. However, you don't see an asymptote on this particular graph down here because if you simplify the function, there's actually an x plus 2 on top, so it cancels out. So the graph is just the graph here of what's left, y equals x minus 1, which is a graph that starts at the y-intercept of negative 1. It has a slope of 1 over 1 because we got a number 1 in front of this x, so it's up 1 over 1, up 1 over 1. A graph you've seen before. However, at x equals negative 2, notice there's a circle, there's a hole or a break in the graph. So when you get a discontinuity that actually cancels out of the function, you end up with a hole in your graph. So it's going to be a line that's graphed, but there's a point where it breaks. It's not there. The big thing to remember when you're doing any type of problems like this, you always want to keep in mind that you can't have a denominator of 0. So no denominator in a rational function can be 0 because division by 0 is not defined. So division by 0, not a good thing. That's what's going to produce those points of discontinuity. All right, let's look at a problem here. And number 1, we are going to try to determine where there are some vertical asymptotes or holes in the graph for this one. So when you're doing these, first thing you want to do is factor both the numerator and denominator if they can be factored. Sometimes it can be, sometimes it can't be. This particular problem we can. We're going to factor both of these. Let's start with the numerator. In the numerator, that's one of those difference of squares one, x squared minus 1. So we want to figure out what is going to multiply to negative 1, add to 0. It'd be negative 1 and 1. So the top factors to x minus 1, x plus 1. Now let's look at the denominator. What's going to multiply to 5, add to negative 6? That would be negative 5 and negative 1. So the bottom is going to factor to x minus 5, x minus 1. Once you've figured out the factoring, then identify the domain restrictions. Remember, that's in the denominator. Where in the denominator would we get division by 0? 2 places. X minus 5 cannot equal 0. X minus 1 cannot equal 0 for our domain restriction. All right, so if we solve those, that means x cannot equal 5, x cannot equal 1. Those are going to be 2 bad points. Now we got to figure out 5 and 1, are those asymptotes, vertical asymptotes, or are they holes in our graph? Well, that's where the next step comes in. Simplify if possible. If we look up at our graph, can anything simplify here? Yeah, we can see x minus 1, x minus 1, those would cancel out. So what's left is x plus 1 over x minus 5. X minus 1 is no longer in our denominator. So this x minus 5 part, that's going to be a vertical asymptote. We're going to have a vertical asymptote. At x equals 5. At x equals 5, there's a vertical line that's going through. Now the one that canceled out, that's going to be a hole. There's a hole in our graph at the one that canceled out, x equals 1. X equals 1, where x equals 1, there's going to be a hole in our graph. All right, we'll pick up with the rest tomorrow and look at some other ones where we're going to try and figure out, is there vertical asymptotes or holes in our graph.